Okay, this is whatever in the previous class it has been covered. Semiconductors, there are two varieties of semiconductors: intrinsic, pure semiconductors; extrinsic or impure semiconductors. Pure semiconductors, either it is germanium or silicon, is a good example. And if you want to convert into the extrinsic semiconductors here, we are supposed to add some amount of impurity. The addition of impurity is called by the name the doping. The added impurity is called by the name the doping agent. And the doping must be done in the ratio of 10 to the power 8:1. And doping agents can be divided into two categories: pentavalent impurity and trivalent impurity. Pentavalent impurity, antimony, arsenic, phosphorus, or any other thing which is having the 5 valence electrons in it. Trivalent impurity means it must be containing the 3 valence electrons. And examples: indium, gallium, aluminium, boron, like that. Intrinsic semiconductors means what? Why we are not using the intrinsic semiconductors? Intrinsic semiconductors at 0 Kelvin, which is not having any free electrons, which is not at all conducting at 0 Kelvin. Therefore, we are not using. Why it is said to be? How it is said to be? Germanium crystal, which is containing the germanium atoms. Each germanium atom is having the 4 valence electrons. All the 4 valence electrons, they are all involving in the 4 covalent bonds here. Hence, free electrons available is equal to 0. If you want to get the free electrons here, either we have to apply the voltage or we have to heat that. External temperature must be acting on that. Due to that one or two covalent bonds are breaking up. If one or two covalent bonds are breaking up here, the electron can move. If one electron, if it is moving here now, that is a free electron. If an electron is moving here, there is a vacancy is created. That vacancy is called by the name hole. The vacancy is having a deficiency of an electron, hence which carries positive charge. Electron, it has been moved here, and hence electrons carries the negative charge here. So therefore, number of electrons is equal to number of holes. Current due to the electrons, current due to the holes, these two are equal to each other. And hence, the current due to the electrons and current due to the holes are equal to each other. Number of electrons is equal to number of holes here. Therefore, intrinsic semiconductors, it has no use. Now, intrinsic semiconductor, germanium or silicon, it can be converted in the form of extrinsic semiconductors either by the addition of pentavalent impurity or by the addition of trivalent impurity. Extrinsic semiconductor can be divided into N-type and P-type depending upon either pentavalent impurity or trivalent impurity, whatever we are going to add it here. Intrinsic semiconductors, either germanium or silicon, to which we are adding a pentavalent impurity, then we are going to get an extrinsic semiconductor of type N-type. N-type extrinsic semiconductor we are supposed to get. One more question. How to get N-type semiconductors? To an intrinsic semiconductor, we are supposed to dope a pentavalent impurity, then we are getting an N-type semiconductor. To an intrinsic semiconductor like that of germanium, if you are adding a trivalent impurity as a doping, then the resultant extrinsic semiconductor is called by the name the P-type semiconductors. Now, in the case of extrinsic semiconductor, N-type and P-type, what is happening here? Now, see that for a germanium crystal, which is containing germanium atoms, which are all electrically neutral, if we are adding an electrically neutral another external atom, which is a pentavalent atom, arsenic, if we are adding, this is electrically neutral because it is an atom. This is electrically neutral because it is said to be having only the atoms. Atoms to which if we are adding another atom here, then we are getting an electrically neutral N-type semiconductor. So one more question. N-type semiconductor, what it is having the charge? The charge of an N-type semiconductor is equal to 0 because atom is electrically neutral. These atoms are also electrically neutral. The resultant N-type semiconductor is also electrically neutral, and we are supposed to add this arsenic atom to the germanium crystal in the ratio of germanium atoms. If it is 10 to the power 8, arsenic atom, whatever we are adding, is equal to 1. In that ratio only we are supposed to add. Now, in the case of N-type semiconductors, what is happening here? We had to analyze, understand about the N-type semiconductors. To a germanium crystal, if you are adding one arsenic atom, because we had to add one arsenic atom here, depending upon this ratio, 10 to the power 8 is to 1. Then each germanium atom, it is containing 4 valence electrons. They are all involving in covalent bonds. If you are adding an arsenic atom to it, then arsenic is a pentavalent impurity. Since it is a pentavalent atom here, which is containing 5 valence electrons, into mark I have written. Okay, these 5 into mark representing the electrons belongs to arsenic. Therefore, this dot mark representing the germanium atoms, electrons. The electrons belongs to germanium is represented by the dot mark. Into mark representing the electrons belongs to the arsenic. Out of the 5 valence electrons which is having by the arsenic, the 4 valence electrons are involving in the 4 covalent bonds with the neighboring germanium atoms. But arsenic, which is having one surplus, one extra electron here. This extra electron which is attached to this arsenic, but it is not involving in the covalent bond. Since the covalent bond or the stronger bond here, not so easy to remove this. But if you are giving a lesser energy here, this free electron, even though it is attached to this arsenic atom, can be possible to remove. I can call it by the name the binding energy. Take your nuclear physics and read about the binding energy concept. The electron, whatever it is revolving around this nucleus of the arsenic nucleus, which is loosely bound. But whereas here, these electrons are strongly bound because of the covalent bonds. But this electron is said to be having lesser bonding is present here. Lesser binding energy is present here. Therefore, if we are applying a lesser energy here, instead of these electrons here, this electron can be easily removed from that particular atom. But it can be removed from that atom only, but it can move from one atom to another atom. That electron is called by the name free electron. That electron is called by the name the free electron. If you are adding one arsenic atom, you are going to get one free electron. If you are adding one arsenic atom, you are going to get one free electron. Don't forget, by the addition of an arsenic atom, pentavalent impurity. Now, going back to the intrinsic semiconductor concept, this crystal, it has been kept in the atmosphere. As this crystal is kept in the atmosphere here, due to the temperature, 1 or 2 covalent bonds are breaking up. Let us consider 2 covalent bonds are breaking up due to temperature. Let us consider due to temperature, 2 covalent bonds are broken up. If 2 covalent bonds are broken up here, you will be having here 2 electrons and you will be having 2 holes. 2 pairs are going to get produced. If 2 covalent bonds are, if 1 covalent bond is breaking up, 1 electron, 1 hole is going to get produced. If 2 covalent bonds are breaking up here, due to external temperature, some covalent bonds are breaking up. Let us consider 2 covalent bonds are breaking up, which is containing 2 electrons and 2 holes. Now let us consider here for this crystal, we have added 10 arsenic atoms. So we have added 10 arsenic atoms. Let us assume like this. As you are adding the 10 arsenic atoms in this ratio, then this 1 arsenic atom produces 1 electron here as a free electron. 10 arsenic atoms donating 10 number of electrons here as a free electrons. Therefore, totally altogether here we are having 10 plus 2, 12 electrons, and we are having 2 holes. Therefore, this N-type semiconductor, which is containing 12 electrons as a free electrons, 2 holes as the holes, positive charge. Electrons carries the negative charge. Again, I will repeat, just you see that even though electrons are having negative charge here, 12 electrons are coming out from this arsenic atom. Therefore, N-type semiconductor which is containing here 12 electrons, number of electrons are more. As a free electrons, number is more, whole number is less. Whole carries the positive charge, electron carry the negative charge. If they are asking the question, N-type semiconductor, which type of charges it is containing? If they are asking, you should not say negative charge. You should not say negative charge, even though the electron number is more, because that electron belongs to this arsenic atom. N-type semiconductor is electrically neutral, but we can say N-type semiconductor, majority charge carriers are electrons. N-type semiconductors, majority charge carriers are electrons, minority charge carriers are holes. This carries 1 mark. Okay, what is that question? Write the majority charge carriers in N-type semiconductors. In N-type semiconductor, majority charge carriers are electrons. Minority means lesser in number. Minority charge carriers are holes. Both are charge carriers here. In this case, due to this, I can write here number of electrons is greater than the number of holes. Electric current due to the electrons is greater than the electric current due to the holes, because number of electrons are more here, number of electrons number is more here, whereas the whole number is less. Majority charge carriers are electrons here, minority charge carriers are holes in the case of N-type semiconductor. And N-type semiconductor, even though the electron number is more, which is electrically neutral. Just I will summarize, just to see that germanium crystal is present. 4 germanium valence electrons are involving in the 4 covalent bond. That is the N-type, what is that? Intrinsic semiconductor. As you are adding an arsenic atom here, arsenic atom, if you are adding one arsenic atom, it is containing 5 valence electrons. Out of that, 4 valence electrons are involving in the covalent bond with the neighboring germanium atoms, but it is containing one more electron, belongs to arsenic. If you are applying a lesser energy here, then this electron can be easily removed from that orbit, and hence it can move from one atom to another atom. That electron is called by the name free electron. Now, due to external temperature here, 1 or 2 covalent bonds are breaking up. Let us consider 2 covalent bonds are breaking up with germanium and germanium. Because of the 2 covalent bonds, there are 2 electrons and 2 holes are produced. Due to this 1 arsenic atom, 1 free electron we are getting. If you are added with this ratio, if 10 arsenic atoms are added here, like this, we are going to have 10 number of electrons. This free electron number is 10 here, and covalent bonds are breaking up. Due to that 2 electrons are there. Totally, we are having 12 electrons, and totally we are having here it is 2 holes. Therefore, number of electrons is greater than number of holes. Whereas in a pure intrinsic semiconductor, number of electrons is equal to number of holes. But in N-type semiconductor, number of electrons is greater than the number of holes. This is for N-type semiconductor. And one more extra concept for your CET examination, I suppose to explain. What is that? For an N-type semiconductor here, let us consider N-type semiconductor. Whatever we have added the impurity here, added impurity, either it is arsenic or something else. That arsenic or something, whatever the added impurity, which is a pentavalent impurity. This is pentavalent added impurity. This is called by the name donor impurity. This is a donor impurity because already we have understood this is donating an electron. This is donating an electron here. Therefore, in N-type semiconductor, the pentavalent impurity, whatever it has been added to convert in the form of N-type semiconductor, that added impurity is called by the name donor impurity, because each one atom donating one extra electron for the conduction purpose. Now, let us have, I said already, for one more question for your NEET exam or something, this is valence band. You are aware of that? Okay, this is the valence band. This is conduction band. there is an energy gap less than 3 eV for a semiconductor. Now donor impurity, this is for the germanium I have written. Now for the donor impurity, if I'm writing the energy level here, the energy level, it lies very close to the conduction band. Here somewhere else. This is E suffix D. That is a donor impurity energy level. This is donor impurity energy level. Where is the donor impurity energy level? Which lies very close to the conduction band. If you are giving a lesser energy, then these electrons can easily jump to the conduction band. That is the meaning. But it is far away from valence band, but closer to the conduction band. This donor impurity, arsenic electrons energy, that free electrons energy, which lies very close to the conduction band. So you are supposed to understand this, because if you are giving a lesser energy, then electrons jump to the conduction band, starts to conduct. That is N-type semiconductor. Now let us go for the P-type semiconductors. P-type semiconductors. What is happening in P-type semiconductor? How we are going to get a P-type semiconductor? First concept. Let us consider it is germanium crystal. For this germanium crystal, we are adding here a trivalent impurity. Trivalent impurity. Maybe it is indium or any other thing. Either it is trivalent impurity, gallium also we can add, indium also we can add, which is having the 3 valence electrons. Then the resultant one is called by the name P-type semiconductor. One more question. How to get a P-type semiconductor? To a germanium crystal, which is intrinsic semiconductor, we have added a trivalent impurity, which is indium. Then the resultant extrinsic semiconductor, impure semiconductor, is called by the name the P-type semiconductor. Now, the thing is, germanium crystal, which is containing germanium atoms, which are electrically neutral. Again, one more question, which are electrically neutral. These are atoms, indium atom, which is electrically neutral. This is also electrically neutral. To a germanium crystal, which is containing germanium atoms, which are all electrically neutral. To an electrically neutral germanium atoms, if you are adding an electrically neutral indium atom, the resultant one is P-type semiconductor, which is also containing only the atoms, not the ions here now. Therefore, this is also electrically neutral. I told you already in the case of N-type semiconductor. One more question. P-type semiconductor, what kind of charges it is having? P-type semiconductor, which is electrically neutral, which is not containing any charge altogether. Because to a germanium crystal, which is containing germanium atom, each and every atom is electrically neutral. Atomic physics, electrically neutral. If you are adding germanium atoms to this indium atom, also we have added here, which is also electrically neutral. Resultant one is P-type semiconductor, which is electrically neutral. This is P-type semiconductor concept. Now, what is happening in the case of P-type semiconductors? I will consider germanium crystal here. I will write germanium crystal. See here, this is germanium crystal, which is containing germanium atoms. Okay. All the 4 valence electrons involving in the 4 covalent bonds. Like this. It is involving in the 4 covalent bonds. It will continue like this. This is one covalent bond, another covalent bond, one more here, one more here. Like this, it will continue. If you are adding one indium atom, to here, then if you are adding one indium atom here, I will write indium atom. This is the germanium atom electron. This is indium atom electron into mark. Okay, that I am distinguished between indium atom electrons and germanium atom electrons here. Let us assume we have added one atom here in the ratio 10 to the power 8 is to 1. If germanium atoms are 10 to the power 8, the added impurity atom, it must be equal to 1. In that ratio, let us assume it has been added. Indium atom is containing 3 valence electrons. Trivalent, 3 valence. The 3 valence electrons I will going to write with the into mark. These are the into mark that I am writing. Okay. These are the 3 electrons belongs to indium. Now, germanium nearby here, it is involving in the 4 covalent bonds. This is germanium. Here, this is another germanium. Okay, here one more germanium. Like this. Here one more germanium. Covalent bond. Here also covalent bond. Here also covalent bond. It will continue like this. Okay, it will continue. Coming back here. 3 valence electrons are involving in 3 covalent bonds with the neighboring germanium atoms. It wants to make one more covalent bond here. Indium, it wants to make one more covalent bond with germanium. Germanium wants one more covalent bond, but indium, which is not containing the electrons here. There is a shortage of an electron here. Here, there is a shortage of an electron because indium is containing only 3 valence electrons. The 3 valence electrons belongs to indium, which is forming the 3 covalent bonds with the neighboring germanium atoms. And germanium neighbor of indium, which wants to make one more covalent bond here, but indium does not containing the 4th valence electron here. It is a shortage of an electron it is possessing here. This shortage of electron is called by the name hole. This is hole. Hole is said to be existing here. Shortage of an electron. This shortage of an electron, how it is going to make it filled up? Some covalent bonds are breaking up here. Let us consider this electron. If it is moving from here to here, hole is creating here. This electron is moving here to here, hole is creating here. This electron is moving here, hole is created here. Therefore, hole is having an appearance for that. For us, it is go on moving. The hole is starts to move from one atom to another atom like that. We are going to see that one. Strictly speaking, electrons only they are moving here. Holes appears to be shifted. As the electrons are moving in one direction, holes are moving in the opposite direction. Okay, this is what is happening here. Now coming back to the summarization of this particular aspect here. To a germanium crystal, if you are adding an indium atom, which is trivalent impurity containing 3 valence electrons. The 4th valence electron, which is not present with an indium atom, hence it produces a hole, means there is a deficiency of an electron. The deficiency of electron will be filled by the neighboring germanium atoms. It will be moving and hence it has been filled. Once it is filled here now indium, which is containing 4 valence electron, therefore indium atom converting in the form of indium ion. Indium atom converts in the form of indium ion. Which ion? Negatively charged ion, because this vacancy has been filled by the extra electron. Indium must be possessing 3 valence electrons only. If this is occupied by an electron here, now indium atom converts in the form of indium ion. Which ion? Negatively charged indium ion. Whereas in the case of what is that? N-type semiconductor, if arsenic loses an electron here, now arsenic, if it is moving out this electron out of this arsenic, then this arsenic loses an electron. Now arsenic atom converts in the form of, as it is moved out. Once it is moved out here, now arsenic atom converts in the form of an ion called by the name one shortage of an electron is present here. It must be having the 5 valence electron. Now it is containing the 4 only. Therefore, arsenic atom converts in the form of arsenic ion, which is positively charged arsenic ion. If this electron moves, if the electron there only is present, it is an atom. If the electron moves out here, now arsenic atom loses its identification as an atom and converting in the form of arsenic ion, which is positively charged arsenic ion. Arsenic atom converts in the form of positively charged arsenic ion. It is a pentavalent. Whereas in the case of the trivalent impurity, p-type semiconductor, if you are adding, here already there is a shortage of an electron. Extra electron, if it is occupied here, indium atom converts in the form of negatively charged indium ion if it is occupied. I hope you understood now. Now coming to the concept. Let us consider due to temperature, external heat energy. Because we have kept this one, we have kept this crystal in the atmosphere here. Due to that atmospheric temperature, maybe let us consider 2 covalent bonds are breaking up. 2 covalent bonds breaks up. Due to this condition here, we will be having 2 holes and we will be having 2 electrons. Because of the external temperature, let us consider 2 covalent bonds are breaking up. 1 covalent bond, if it is breaking up, it produces 1 electron, 1 hole pair. 2 covalent bonds are breaking up, it produces 2 holes and 2 electrons. Let us imagine we have added 10 number of atoms. 10 atoms of indium, it has been added. 1 indium atom producing 1 hole. 10 atoms of indium, 10 atoms of indium atoms produces here 10 holes. Together, if we are adding here, we will be having 2 holes and 10 holes. Together, we will be having, I can say, it is containing 12 holes and it is containing 2 electrons. It is containing 12 holes and 2 electrons. Okay, therefore, in this case here now, number of holes are more than the number of electrons. Hole current is greater than the electron current because the number of holes in a p-type semiconductor, number of holes are more, number of electrons are less here. Majority charge carriers are holes, minority charge carriers are electrons. One more question. In the case of p-type semiconductors, which are the majority charge carriers? Holes. Which are the minority charge carriers? Electrons. The number of holes are greater than the number of electrons in the case of a p-type semiconductor, whereas in the case of an n-type semiconductor, number of electrons are more, number of holes are less. But in the case of an intrinsic semiconductor, number of electrons and number of holes, these two are equal to each other. We don't want both are equal to each other. If they are equal to each other, we have not achieved anything. For that purpose, either we are going for a p-type semiconductor or we are going for an n-type semiconductor. Here, either for a p-type or for an n-type semiconductor, we are supposed to switch over to that. In an n-type semiconductor, majority charge carriers are electrons, minority charge carriers are holes. Whereas in the case of a p-type semiconductor, majority charge carriers are holes, minority charge carriers are electrons. So this is a basic condition, holds good for n-type and p-type semiconductors. So I have covered n-type and p-type only. I am taking up the classes very slowly, one concept only that I am teaching in one day. But if you have forgotten that, I am not bothered. We cannot do anything. Just listen here further. See here, we are asking 2 marks question, something we are asking here. Carefully see here, watch it, read it, write the differences between intrinsic and extrinsic semiconductors. Either we are asking for about 2 marks question, 3 marks question here. Write the differences between intrinsic and extrinsic semiconductors. Read line by line. If you are having any doubt, you can ask. intrinsic semiconductor, extrinsic semiconductors. In the case of p-type semiconductors, the added impurity is called by the name acceptor impurity. The added impurity is called by the name the acceptor impurity. That energy level lies very close to the valence band. I have forgotten to say that. So the meaning here, the added impurity is called by the name the donor impurity in the case of n-type. In the case of p-type semiconductor, the added impurity is called by the name acceptor impurity because it is accepting the electrons. This is acceptor impurity. And here the energy level of indium lies very close to the valence band. This is acceptor. Okay, it will happen like this. This is the valence band. This is conduction band. Now, acceptor energy level is present somewhere else here. This is EA, A for acceptor, D for donor. Energy level for the acceptor means indium atom, whatever the electron, hole is present, that energy which is close to that of the valence band. Valence band, electrons can jump over here easily. For that purpose, it has been present like this. Okay, first you go through this. Another 3 or 4 minutes time is there. There is no permitted energy state between the valence band and the conduction band. Here, permitted energy state means this is, you see that. In the case of ED or maybe EA, which is present between the valence band and the conduction band. This is applicable only for, this is applicable for p-type, this is applicable for n-type. Both are extrinsic semiconductor. Whereas in the case of an intrinsic semiconductor, this energy level, it is not coming at all. This is not coming. Only valence band is present, conduction band is present. Valence band is present, conduction band is present. This energy level is present. In between energy level, one more is present here now, either for the donor or for the acceptor. That is applicable only for extrinsic semiconductors. That is the meaning here. That is the meaning here. Okay, yes. Another 3 marks question. Today we'll send all these notes. Write the differences between n-type and p-type semiconductors. Write any 2 differences, 2 marks. What are n-type semiconductor? What are p-type semiconductors? 2 marks question we are asking here. I will send the notes today only, Pooja, no problem. If it is not so clear, okay, you can see crystal clear image in your Google, the whole notes. Because these things are written with the small letters, therefore you are not going to see that. NH is greater than Ne, Ne is greater than NH. Number of electrons are greater than number of holes, number of holes are greater than the number of electrons. I will send it today. Today I am free, I will send it. Okay, Pooja.